我多撞我，我撞我。我擦伤，两个人吵。报警，我要给钱，他要给钱。
不用啊，那你不给钱啊？要报警200。你要知道被他骗你啊，他错，他撞你了，就是这样。
他一下子出现在我旁边，
有可能
不可能，因为我们从来没有看到他。
因为第一种哦，你信号，但是你没有看你的声音。
啊？没有啊，问题是没有，他是撞在我的那个平行的后面那个位置，他撞到了他。
有车了，然后对面一个萝莉，我们讲那个萝莉前面有车，那个摩托你的背后，我根本没有看到那个摩托。
他充几块？
哦，我也嘛，那个他又啷个的啊，又该啊。
真的。
他还在吃这的时候，还看着那个路口。
啊，有撞过车，但车真的穿插到那旁边。啊？什么？这种经验不可以太大。
我是没那么开始这样。
啊？那你。
我那个路边啊，路边到不得啊，家里面做的，
算家里面，
不好吃的，
好吃还可以啊。
还饭是要加钱的，
要加钱，但是卖完了。Testing. Let's start first. I want to do some errata from the one that we discussed last time about assignment 2 question 4B. Okay, so if you remember this question, we want to prove that the union of two subgroups of a group is not a subgroup unless one is contained in the other. Okay, so I want to discuss about the logic about on these unless first. So let's dissect this statement here. So let's make everything before unless Q, and then everything after unless is P. Okay, so this is a type of statement which is Q unless P. Okay, so so what's the logic of this Q unless P? So let me give you some scenario and then we can try and discuss what's going on. Okay, so let's discuss. So let's give you some kind of Q unless P, a real life statement here. For example, I will go for competition. Okay, unless it rains. Okay, so let me ask you, if you heard about someone telling you this statement here, what do you think? What do you think? What's the first thing you think about? When will this person go to competition? If it doesn't rain, if it doesn't rain, then I will go for competition. Any other interpretation on this statement or not? What does this mean? I will go for competition unless it rains. If it rains, what happens? I won't go. Okay. So this, if you I won't go if I will not. So if you look at both this statement, right, these will give you what? A biconditional statement here, if and only if. Okay? If and only if. I will go for com if and only if it doesn't rain. Okay, so this is a biconditional. There's another way of looking at this question, right? What way? Either I go, either it rains, but not both. Okay, so maybe there's another choice is either it rains. Okay, so yeah, so I will go for competition or it rains. Okay, but cannot happen together, but not both. Okay, so this is what? This is a exclusive or. So this is a typical language that people will how to say acknowledge. So you carefully so that's why what I gave you here, these two statements is different but it's referring to the same statement. So you need to be careful when people talk to you or when people want to tell you something, which one they meant. Okay, so now today I dissect for you these two cases. What happens? Okay, if you write down the truth table, what do you get for the first one? Okay, so first one we understand it as a biconditional. Let's see what this truth table is. So we have P, we have Q, we have if and only if. Okay, in the first case. Second case, we have exclusive OR. So exclusive OR, sum notation will put P direct sum Q. Okay, P plus a circle Q. So what's the truth table here? Let's put down all the possibilities. So true, 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 false, false, true, false, false. Okay, so P if and only if Q meaning what? You will get true, false, false, true. But exclusive OR, so let's write down all of them again. So only when one true is true. Okay, so what can you see here? Can you compare the two truth table here? One is true, false, false, true. One is false, true, true, false. So meaning what? These two possibility is negation of each other. Okay, so these two possibility are negation of each other. So it's quite important you try to understand what people say here. But for our mathematics, we don't choose between these two. Okay, we will choose number 3, P or Q. Okay, what's the truth table for P or Q? So let's write down P or Q. P, Q, true, 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 false, false, true, false, false. So we'll get true, 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 false. So one true more than the other two cases. So this is what we chose for unless. So meaning what? Meaning I will go for competition. Okay. Unless it rains. Meaning what? If it rains, I can go. Either I can go or I don't go. Both could happen. I don't throw out the other cases. Okay. In other words, you also can prove that this is logically equivalent to not Q implies, not P implies Q. Okay, not Q implies P. Sorry, not P implies Q. Okay. So if it doesn't rain, I must go. I must go. Okay, if it doesn't rain. Otherwise, this statement is useless. But if it rains, I can either go or I either not go. Both can be true. Okay, doesn't contradict this statement. Does it make sense? Okay, so given this, what do you need to do here? Okay, so you should either prove P or Q, or you should prove not P implies Q. Okay, you should do these two. So actually Q we discussed already. If you want to prove Q, you just give a counterexample. But how about P? Okay, if Q is not true, you need to prove P. But not Q implies P is just not P implies Q. It's the same. So this is the case that you need to produce in your assignment. Okay, maybe I can quickly go through for you since you have one more there. So let's say if it is not contained in the other, what happens? So let me quickly go through the answer, but you don't copy, you write in your own word. Okay. So suppose one subgroup, or suppose one subgroup is not contained in the other. Meaning what? Meaning there exists H1, H2 as a subgroup of G, such that H1 is not a subset of H2 and H2 is not a subset of H1. Okay. So if you really want to be really precise, you can put an N here. So sometimes I put comma, actually N is the same. Comma and N. If you really want to put everything as a logical operator here. Okay. So if they are not subset of each other, what can you do? Then we can pick an element from the complement. Okay, let's say we pick A1 from H1, take away H2, and an element in H2, take away H1. Correct or not? Does it make sense? I mean, in your high school, right, you can draw a Venn diagram like that. Okay, H1, H2, like that. Okay, one is not contained in the other, so there must be something like this. Okay, make sense? Okay, so, well, what do you want to show? Okay, you want to show that union of two subgroup is not a subgroup. Okay. So maybe you can try to draw some contradiction here. So assume H1 union H2 is a subgroup. Okay, usually when we talk, when we do this kind of contradiction, we assume something for contradiction. Our rule is to write, assume that this is a subgroup for a contradiction. Okay, you're telling people, I want to assume otherwise. Okay, otherwise people will think weird. Hey, why you assume otherwise? Because you need to tell people, oh, I'm trying to do a contradiction now. Okay, I'm trying to achieve a contradiction. So you assume for contradiction. Does it make sense? Okay. Otherwise, people will be shocked. Why are you assuming the result is not true? Okay, so we are preparing for contradiction. So since H1 union H2 is a subgroup of G, so what? If you look at A dot B, what happened? A is in where? H1. Automatically, it is in the union. B is in H2. Automatically, it is also in the union. So if it is in the same set, what can you do? Multiply them. And since this union is a subgroup, meaning what? It is closed under multiplication. Okay. So this product here is inside the union. So where to draw contradiction? If you want to draw, if you ever want to draw contradiction, you need to hold on your assumption very well. Okay, so what's the head assumption here? This A and B here. Okay, can we draw some contradiction to where A and B live on? Okay, because we say that A live in H1 but not H2. Can we make A live in H2 or not? No, don't know. Try. Okay, can we make B live in H1 or not? Okay, we try. Okay. Let me tell you one thing. So the question that I'm gonna set like for your exam or what, this kind of contradiction is easy to drop from the assumption you have in your question. Because in real life, in our research, this contradiction is not easy to get. Maybe you need to deduce some more property and then contradict that property. So it's kind of like hidden. Okay, so whatever we did now is relatively easier. So you need to try and understand the question, every word you should understand. And then the property that you need or contradiction you need is just sitting inside that question. Okay or not? Yeah, most probably it's like that. Our research is second level. I gave you the property, you maybe need to deduce more property, okay, to contradict. Okay, so where's the contradiction here? Okay, so we will play with a definition, okay, of this set. So what does it mean by A dot B is in the union? It means what? It means that A dot B either is in H1 or A dot B is in H2. So can you try and guess what's the contradiction here? H1 is a subgroup, H2 is a subgroup. So what? Huh? So what? Let me let you think a few seconds. What kind of I'm claiming that contradiction you can find here inside this section. Huh? You can take inverse. What sort of inverse you can take? A inverse. Where does A inverse live? H1, right? Why? Because A live in H1. H1 is what? Subgroup. Every element must have inverse. So in this case here, if A dot B is in H1, then A inverse times A dot B is also in H1. But what is A inverse A dot B? By associative, it is just B. Meaning B is in H1, which is a contradiction. If this is not the case, if the other case is true, what can you do? What can you consider if the other case is true? You can consider B inverse here. Why? Because B live in the subgroup H2. Okay, and then you take the product, it close under multiplication. But what do you find here? A, B, B inverse is what? It's just A. A is in H2, again, a contradiction. Okay, so in both cases, we achieve contradiction. Okay, go back and digest this solution. Write on your own word. Write your own words. Okay, any question so far? Question? Any question? Any question so far? Is it clear? Any question? Okay, no question got actually got two response. Okay, one, either you understand, two, either you don't understand. Okay, so if you don't understand, if you don't want to ask now, you think again, then come back for office hour or message me or email. Okay, and then you need to do tutorial exercises. Okay, don't just do assignment. It won't help much because mathematics you need practice. Okay, you need a lot of practice to make your concept live inside your brain. Okay, not just calculating. Does it make sense? Okay. One thing to see whether you learn something or not is whether this thing will stick in your mind forever or not. If you understand certain thing, that thing you won't forget one. Okay. Yeah. Okay. Okay. Yeah. Any question? Any question? Anyone is doing arting extra solution or not? Hey, wait, it's Hao Tian. Hao Tian not here. Tian not here. Han Ping, how much you try already? Several? Okay, good. Yeah, you can come and check solution with me later if you like. Okay. Yeah. Any question to the previous lecture notes? I have some typo and then I keep fixing it. So make sure you download the latest one. There will be the date time when I upload it, so you know when I the last update the notes. And then any one of you uses the typeset lock or not? The typeset one, the latex one. No? Read my notes. Okay. I mean, if you read it, maybe you can check whether there are any differences or not, or discrepancy. If you found any, you can find me. So our goal, my goal is to these lecture notes typer. I think my goal is we will do a proofread before midterm, so that everyone, if you want to have a PDF to do revision, you can use it. Okay. So maybe we will do it by this week or next week, and then we will release a relatively complete version for your midterm to do revision. Another thing is, if you look at your teams, right? I think Shaoqi, right? Shaoqi post out what? Bonding meeting for this Saturday. So if you are interested to join, you can try and find your own transport around among your classmates. Okay, so they are going to have a dinner at where? Utah Sungai Long, opposite Utah. Yeah, opposite Utah. So if you really want to go, but you cannot find transport, so you can try and find Shaoqi or Pansing. We can try and figure out how. 看苹果看，没有发给你。It's in the Teams. Teams. It's in the Teams. It's in the abstract algebra Teams group. Okay. Yeah. Okay. So if you are interested, you can contact Pansing or Shaoqi. Right. It's about. By the way, it's a mukata. You know what's mukata? Yeah, it's a Thai buffet. Okay, buffet. So Thai buffet is 29.90 cent, 29 cent per person. Okay, just yeah, doing promotion. No, okay, yeah, 29.90 per person without seafood. Okay, with seafood is a bit more
你是否
expensive.
他老板？
Suggested by Tan Xing.
No.
She said it's nice, so we should go and try it. Huh? No, next time. If I got my bonus, maybe. 真的？什么？ Yeah. Of course. Okay, so if there's no question, you can leave it to later. We will recall what we have last time. So let's recall what we have last time. Let's continue with our story of group homomorphism. Okay, so let's see how does a generic group homomorphism looks like. Okay, generic is like 最普通, I mean 最 general. Okay, generic group homomorphism. So listen carefully, Jia Ling. So we start with a domain and codomain. Okay, domain and codomain. So usually I denote domain as G and then codomain as G prime. Okay, we start from a group. And then we have a group homomorphism. Okay, that's quite clean. So what have we studied last time? So if you take a bunch of element of G, let's say x1, x2, x3, x4, okay? So we can basically map them across, right or not? Okay, we just look at the what? What does it call? Let's say they all map to the same person, x prime. Okay, so this is a image of the set. Image of x1, x2, x3, and x4. Or in other words, what are these x1, x2, x3, x4? These are the pre-image of x. Okay. Oh, here maybe I can add vx1, vx2, vx3. So okay. So if you look at the image of the whole group, okay, what do we prove about this image here? This image here is actually what? Is a subgroup. Okay, image of a group is a subgroup. So maybe which way should I point? Maybe just point to the word, it's easy. Okay, image of a group is a subgroup. And what else we prove? Actually, I asked you go back and prove it. So if you take a subgroup here, you look at what gets sent to this subgroup, meaning what? I look at the pre-image of this subgroup is again a subgroup. Okay, so homomorphism is nice. It sends subgroup to subgroup. And subgroup to subgroup. And then one last thing we prove is a very special subgroup in G called what? A kernel. Okay, let's call this a kernel. What happened this kernel? What happened to this kernel if you apply phi? What do you get? You get the identity element here. And we also prove that this kernel is also a subgroup. Okay? Does it make sense? Okay, so this is a generic picture that you should have inside your mind. Okay, pre-image, image, kernel, and subgroup. Okay, so this is a general picture you need to have in your mind. Okay, so far, so good. Okay. So next property here, we'll continue to explore our kernel. So we'll say that a homomorphism P G to G prime is injective, okay, or one-to-one if and only if the kernel, okay, let's call it K or kernel of phi to be the identity element here. Okay, so meaning what? Meaning what? If your map is one-to-one, if you look at the kernel of your map, there's only one thing inside them. It is the identity element. Which means what? This kernel is a trivial subgroup. Okay, only one gets sent to identity. This is very important. We'll keep using this property again and again in group theory or ring theory. Okay. Very important property here. Right. So there are two directions here. So let's do one of them first. So which one we do? Any preference on preference? Okay, let's do left to right. So like what I tell you, algebraic proof is relatively straightforward. What do I mean by relatively straightforward? Just spell out all the definition, okay, inside this statement. And then you just try and arrange these definitions together. Okay, so there are two things here, right? One is injectivity. Okay, more than two things. So injectivity, homomorphism, and then kernel. Right. So let's suppose our homomorphism is injective. Okay, what do you want to show? Very important. In pure maths, you need to remember your goal. Okay, so what's your goal here? Want to show that the K is the trivial subgroup. So, meaning what? You want to show a set equality here. Okay, so what's this set equalities here means? So you need to show that K is a subset of 1, and then 1 is a subset of K. Okay. So obviously 1 is a subset of K. Do you remember why? There are three properties we show about homomorphism, even before we use injectivity. Homomorphism satisfies three properties, very important property. What's the three property? You can split the product of n elements. And then what else? Send identity to identity. Ne? So this means what? This identity is in the kernel. Okay. The third thing is send inverses to inverses. Meaning what? Phi of A inverse equals to phi A inverse. Okay. The inverse of phi. Right. So first, one direction is easy because we know that phi of the identity in the domain is the identity in the codomain. Okay, so one direction is proven last time. Okay. Why easy? Actually, we proved it last time. So actually, there's work inside there. Nothing in this world is easy. We have done the work before. So if ever there's anyone tell you something is easy, it's a scam. Okay, it's a scam. Nothing is easy in this world. It's just that you have done the work early. Yeah, it's really a scam. Okay. Okay, how about the other case? The other case, what do you need to show? Everything in the kernel have to be 1. Okay, so a bit challenging. You want to show that everything else that happen to be in the kernel have to be 1. Okay, a bit challenging. So we just take what? So second, consider x not equals to 1 in K. Okay, let's take other elements inside this K here. Okay. See if we can show that this x is 1 or not. Okay, if I can show that all the x has to be 1, then there's only one thing inside it. Does it make sense? Does it make sense? Agree or not? Okay, I take any element inside this K, and I want to show that this element has to be 1. Then only 1 exists inside it. Consider x is not equals to 1 in K. Suppose we can do it. Okay. And then this x should satisfy what? Phi x equals to 1, right? Because it's in the kernel. But what do we know? There's assumption we haven't used. Phi is injective. Okay, phi is injective means what? Since phi is injective, what do we know? What's the definition of injectivity? You must remember this one. Cannot forget one. Meaning what? If your image is the same, it implies that the pre-image is the same. Okay? A lot of people confuse what? They swap this arrow. But swapping this arrow is really trivial, It just says what? Same thing gets sent to the same place. This is what function does for you. You don't need go injectivity. So meaning what? Injectivity is another direction for your function. Does it make sense? Okay. Right. But what do you know? But you know that phi1 is equals to 1. Also, in this case, phi x is equals to 1 also. Meaning what? Actually, we have x has to be equals to 1. You think that it's not 1, actually it has to be 1. Okay. Does it make sense? Okay, so it follows that everything inside the kernel is in the set of containing the element 1. Hence, K equals to set containing. So can you see the structure of this proof or not? First half of the set inequality says what? We use what? We use homomorphism here. But the second part really needs injectivity. Okay, so we are really using the what? The assumption to its fullest. Okay, we use everything we know. Okay, so mathematics statement is like that. We won't, how to say, we will keep everything simplest, in the simplest form. we won't include any any unnecessary condition inside our statement. So whenever we ask you to prove a statement, every property will be stated. So make sure you use it. Okay, in principle, it's like that. Right. Good. So we still have the other direction to go. Okay, so we want to suppose that the kernel is the trivial subgroup, and then we want to show that phi is injective. Okay, so how to show phi is injective? We want to show an if-then statement. So if we want to show if P then Q, obviously we need to suppose P first. So in this case, suppose phi x equals to phi y. Okay. So this phi xy is taken from any xy in G that satisfy this property. And then what do we want to show actually? We want to show that x equals to y. Okay, we want to show that x equals to y. So how do we go about doing this? How do we go about doing this? So you don't just think plainly, you need to have something inside your mind. So what does this k equals to 1 means? At least you know what phi of identity is identity. Okay. But here is a form of phi x equal to phi y. So can you make it into some form like this first or not? Meaning you put phi onto a same side. Can you do it? Can you do it? Inverse. Good. Which inverse you can take? Huh? You can multiply both sides with what? Phi inverse y, for example. Okay. But what is this phi x times phi inverse y? Can we combine or not? Can we combine? But one is phi, one is phi inverse. No? So how? We can move inverse into the element, right? I don't know. Okay, so this is a nice thing about homomorphism. We send inverse to inverse, right? Phi y inverse equals to phi inverse y. Okay, and then now we got two phi now, meaning we can combine. After you combine, what does this mean? This is a new guy inside your kernel, xy inverse. But what did you know about inverse? Only one exists. So meaning what? By assumption, xy inverse must be equals to the identity, which means what? S equals to, okay? Does it make sense? Yeah, so we use a cancellation law a few times, and then we use homomorphism. Okay, and then group property. Okay, so very nice, very good structure, very nice structure. Any question with this proof? Yes. Yeah, so we check it for all xy that satisfy this condition here. Okay, this is the definition for injectivity. If phi x equals to phi y, all the xy that exists such that, okay, if for all xy that satisfy phi x equals to phi y, it implies that x has to be equal to y. This is the definition. Yeah. So you need to be careful whenever you read definitions. You look at this variable, right? X, y, z, or epsilon, or delta, or anything. You need to put quantifier one. If the quantifier is for all, or there exists, they are really different things, They are really different. You need to be extremely careful. Actually, especially in your analysis, it's very dangerous, very dangerous when you see all these together. Does it make sense? when you put all these things together. Because if they are order swap, it's referring to different things. For example, right, continuity is what? For every epsilon, for every x, there exists a delta, such that for every point that is delta close to x, f of that point minus fx is less than epsilon. But what if you swap for all x and delta? The continuity definition becomes uniform continuity. Okay or not? So if you change these quantifier in order, that means different things. So you need to be really, really, really careful and have to be sensitive to this quantifier. Okay, maybe sometimes you don't see quantifier inside your definition. Actually, it is implicit. Okay, maybe it means for all. Usually it's implicit sometimes. So be careful. For example, sometimes you see whenever, if, or what. Okay. Yeah. No need to tell them also. Don't fall into the trap. Yeah, don't fall into the trap. Be careful. This quantifier. Right. So one example I give you last week, right? What homomorphism is injective? Do you still remember I think I gave you 6 examples of kernel, right? Any of the kernel is trivial or not? I do revision. Where is it? So first kernel here got something else, SLN. So you can see that in this SLN, right, there is more than the identity element. Can you find other SLN matrix on other than identity element? And even permutation, obviously you can write more than the identity element. But in this third line here, right, I said that the kernel of this exponential map is 0. Okay, so meaning what? This map is injective because the kernel is a trivial subgroup. And for the rest, it's not trivial subgroup. Right? Is it obvious? So something more than the identity inside other set. Okay. So I mean this thing about injectivity, right? Actually, you should see from your MA, right? Did you guys introduce exponential function? Or maybe you should do soon. Already do Not yet, not yet. Okay, probably you need to do soon. I think the way they argue is it is an increasing function, so you can prove that it's injective. But now we're gonna prove it group way. Okay, use group to prove. Use homomorphism to prove. Okay, we don't see it as a continuous function now. Okay, we see it as a group homomorphism. This is how to say, this is, I wouldn't say better than the analysis, but there's more structure here. In analysis, you only know about length. Okay, the distance. Okay, if you go further, you learn something called metric. Metric is distance. So you know how to measure the distance on R or Rn like that. What you learn, the easiest distance is Euclidean distance, Euclidean matrix. Okay, the Pythagoras theorem, for example, is a Euclidean metric actually. But now we know how to compose elements in a domain and codomain. And then somehow this continuous function, right? Remember the multiplication, respect the multiplication. Okay. Yeah, we have more things than continuity here. It is actually a homomorphism, you can tell Prof. Teo. Okay, okay, right. Joking. So this homomorphism is injective. Okay, so I give you an example of injective homomorphism. Okay. Okay, so far so good. Okay, or not? Yeah, so this is the kernel that kernel can detect this injectivity. So if you found that kernel is non-zero, then it's not injective. Okay, so when you ask about injective, You don't need to go to the definition if you know about kernel of that map. Straight away go and check what's the kernel of that map. Right. Okay, so if there's no question, we continue with new definition here. Sorry. Addition. Yes. So here use addition. Okay. Yeah, 0 is in here, so that's why e to the 0 is go to the other identity. So new definition here. So suppose we get 2 elements in G, then what can we do? We can do an operation, okay, which is G times A times G inverse. This is called the conjugate of A by G. Okay, so this should be familiar to you. It's not by accident. This is a generalization of the diagonalization. Okay, this is a generalization of it. For example, you have seen in linear algebra, right? So if we take G to be GLNR, so meaning invertible matrices, what do you define? What does Ali define for you? Two matrices A, B are similar if there exists an element in G such that A equals to DB, D inverse. Okay, so this is similar. This is very general. But what you learn in LA is this B is special, right? It's a diagonal matrix. So you ask when is it similar to a diagonal matrix? And it turns out that it is a eigen values of your matrix. And then you use what? You use eigenvector to build your D. Okay, so what? Let me see. Sorry. Yeah. Okay. So so we also motivate by this example here. We will say that, let's say, what does it mean by A is a conjugate of B? Okay. So what does it mean by A is a conjugate of B? If there exists a group element such that A equals to GB G inverse. Okay, so we don't use similar anymore. Okay, we just use conjugate. They are conjugate of each other. Okay, so you can use G inverse to get the other element. Right, so we're going to define what is a normal subgroup now. So let's define normal subgroup. So I told you about kernel, right? So now is a new group here called normal subgroup. Let's denote it as N. Yes, since it is normal. So what's a normal subgroup here? Right. So what's normal subgroup here? Obviously, this is a subgroup, right? So meaning you need to take elements from G. Okay. So this is N is a normal subgroup if for every element inside N that you pick from G, and you take any element in G, okay, then the conjugate, okay, the conjugate GA, G inverse is in N. Okay. Does it make sense? So how do you check a group is normal? You take any element inside your group, normal subgroup, and then what do? Take any element from your group. So this G might come from outside, right? Inside, there's nothing to talk about because my normal subgroup is always closed one. But this is more than closure. You can take any element, okay, outside this N here, and then do conjugation. We still live inside N. Okay, so you are thinking that you're taking something outside N, but you conjugate it, it stays inside. Does it make sense? Okay. Usually it's not closed, right? If you take element outside the subgroup. Okay. But if you do this conjugation, it stays inside. And then we will call it a normal subgroup. So let's write down some equivalent statement here. So if you know that a subgroup is normal, actually it means what? If you look at G on the whole set, you conjugate the whole set, this is a subset of N. Correct or not? If you collect all the G and G inverse, it should look like this, G and G inverse. And then it is an element of N. Okay, so it's a subset. Okay, so I mean, you need to be flexible between these two expression here. One, I talk about elements. The other, I talk about set as a subset. Okay, you should freely go between these two kind of explanation. Okay, they are the same. So in this case here, an equivalent statement will be equivalent definition of N is that N will satisfy Gn G inverse equals to N for all G in G. Okay, let's see, is this true or not? Okay, is this true or not? We already have one inclusion already. How about the other inclusion? Is it true? Is everything in N right here or not? Why? Don't know. Why? So an equivalence formulation will be N will satisfy this equation here. Okay, for all G. Is it true? So we already have one inclusion already. Okay. How to get the other inclusion? So meaning why N is a subset of G and G inverse. I let you think about 1 minute. How to get the other inclusion? Let you think of it. I can try and discuss with your friend how to get the other inclusion here. Any idea? Sorry? Yeah, I mean, an equivalent definition of N is this thing. So I gave you a definition of subgroup already. But we can deduce that there's one inclusion is always whole. G and G inverse is in a subset of N. So to show equals, what else do you need? You need the other inclusion. So why is it N is a subset of G and G always? Huh? Move from the left to the right. So let's see what we're gonna do here. So are you saying that how to move? Start from where? The right side of the left side. Uh-huh. So what which one you start? You start with what? G and G inverse equals to N. Multiply G on both sides. You want to get something like this. Okay. So what? Yeah. I mean it's I mean yeah, right, correct. But what can you say about this? It's correct, but I mean how it tells you something useful. Do you know how to read these statement or not? It's not just algebraic manipulation here. What does this mean? GAG inverse is in N. It could means that GAG inverse is equal to something inside N, something. Okay, so this equality here says what? Right. This equality here says what? You want to show that two set is the same. Meaning what? You need to show that everything in here is in here. Everything in the left-hand side is in the right-hand side. Everything in the right-hand side is in the left-hand side. Okay, so how about let's keep this first. Okay, let's show this and then we will take a break. Okay, let's do this. So we want to show that. So again, of definition equivalence, right? If you know what we did in the assignment, so we call it definition 1, definition 2, right? Let's do 1 to 2. Again, 2 to 1, I left it for you to do. I think it's obvious. But anyway, so let's do definition 1 to 2. Okay, so what do we know? We already know G and G inverse is a subset of N. Okay, what we left to show is N is in a subset of G and G inverse for all G and G. Meaning what? What can we do here? If you want to show subset, right, obviously you need to show that every element in the left set is in the right set. So you just take any element in N, okay? How to show that this A is inside here? You need to write it as what? You need to write it as what? G of something times G inverse. Maybe G, there exists a B such that A equals to GB G inverse. So take A in N, we need to find B in N such that A equals to G of BG inverse here. Does it make sense? I need to write it into this form. This is the set of what? G times something in N times G inverse. So what B you can choose here? Any idea? What B can you choose here? What can you choose here? What B can you choose here? To make sure this holds. What is the thing you need to fit inside here so that you get A? Sorry? So we choose B equals to G inverse AG. Correct or not? What happened? So not that. G inverse A, G inverse is what? Is A. Good. But there's one thing you need to settle first, right? What do you need to settle? This B has to live in where? N. But this guy live in N or not? Why? Why live in N? What is N? N is a normal subgroup. What does normal subgroup say? Everything inside the normal subgroup, if I conjugate with element in G, it live inside the normal subgroup. But maybe you ask a question, hey, he's saying this inverse appear wrongly. Correct or not? Appear wrongly, right? Because my definition says what? G inverse. This one is G inverse AG. What do you mean by same? So you can rewrite what? Actually, you can rewrite it as G inverse of A, G inverse inverse. Right, because G inverse is also something in the G. Okay or not? Okay. So B is also in N. Any question? So this is what I asked about you. What do you mean by this N equals to G inverse NG? Because really how we find this B actually is coming from G inverse NG. Okay. Any question? Or question now? So this is the thing that you need to be, this is the technique in abstract algebra. Okay, you can take inverse of inverse and inverse and inverse and inverse again. Okay. Any question? Question? No question? Question? Question from the back? Any question? Okay, let's give you example and then we break. So example will be, so first example, you can go and try and check if you take the special linear group. Oh, I haven't teach you the notation yet. So let's leave a notation for you. So we will denote hash as a normal subgroup of G if hash is normal in G. Okay, normal subgroup in G. We'll say that it's normal in G. The subgroup is normal in G. If the subgroup is normal in G. Subgroup. Okay, so SLN is a normal subgroup of GLN. Can we imagine why or not? Meaning if you conjugate with any non-zero determinant matrix beside this matrix, you still get back the determinant 1 matrix. Correct or not? Is it true? If you conjugate, okay, conjugate the determinant 1 matrix with non-zero determinant matrix, do you get back determinant 1 matrix or not? Why not? GM. So okay, so let's take some guy from here A, some guy here from M, right? So what is the determinant of M inverse again? You can split, right? Because it is a homomorphism. But what do you get? Determinant of M inverse is what? That's why you prove that determinant of M inverse is actually 1 over determinant of M, because if you learn abstract algebra, you know that it is a homomorphism because it's sent inverse to inverse. But how do you prove in LA? Okay, it's not hard also. Here we have properties here. So what is the determinant of what A here? So it's just 1, right? Okay, 1 times 1. So cancel each other, you should get 1 again. Okay, so it still live in the, so meaning what? So meaning M inverse still live in SL and R. Okay, okay. Right. So more things you can check out. For example, even permutation in Xn. True or not? Think about this again. Is it true? If you conjugate by any permutation on even permutation, is it still an even permutation or not? Think about it. Any cycle you split into permutation, into transposition. But when you conjugate on both sides, do you add in an even number of permutation or not? Okay, you add in even number of permutation. Okay, and then what else? Very easy one, trivial subgroup. Okay, this one nothing to talk about. Trivial subgroup is trivial. Do you agree? Because if you do G identity, G inverse is identity again. And then you should check that a cyclic subgroup of N inside Z is also what? Also normal. Okay, but in this case here is even more trivial because here is abelian. Okay, here is abelian. So you can move the inverse to the other side, just cancel. And then what else? Actually, the circle subgroup that I told you that contain root of unity is also a normal subgroup. Correct or not? You should use Euler formula to think about it. Okay, if you conjugate e to the exponent to 2 pi I, multiple of 2 pi I, okay, conjugate by r times some exponent to some argument, right? Cannot imagine. Okay, let me simply write things here first. So anything in x1 should be root like this. So let's write it like this. And then how do you conjugate with complex number here? Complex number looks like what? Only two information that record complex number is the radius and argument, the angle. So r times e to the what? 2 pi I something also. What's this? What's the Euler formula? What's the formula? I theta. I think like this. I theta. Okay, so what's the inverse? Obviously, it's just 1 over r times e to the, I think, minus theta. Guess. Has to be true. Has to be true because when you multiply, it has to be identity. But anyway, it commutes, right? So it cancels out. Okay. What else? Last one. So is Z inside R also. Okay. Yeah. So you should notice one thing here. When I list down these 6 things, actually you see it before. It's the kernel of some homomorphism. Okay, so the next thing we're gonna prove is if you are a kernel of a homomorphism, then you are a normal subgroup. And then in the end of this group theory stuff, you will learn that every normal subgroup turns out to be a kernel of some homomorphism. Okay, so it's an if and only. Okay. Later we'll prove a kernel is a normal subgroup, and then in the end of the group theory, we'll learn that every normal subgroup turns out to be a kernel of some homomorphism. Yeah. Okay, it's very useful stuff. Right. So let's break until 8:16. 太快 ，OK， 开始要快了啊！
我们现在找到加就是
啊，
就现在
对，可以早上啊，对，
课件往上跑，
，Yeah，
基本上滑到刚刚开始的时候，我是说正文刚刚开始，
耶，
但你去滑到那个等价的证明这个地方，像那个1-to-1和那个的证明。对，差不多就这个地方。你看看你这个负一次写在哪儿？
我负一次写在哪？
那是不是应该写在括号后面才对？
应该是比较好，是放在正括号上面。
不是比较好，我觉得放在这里是错的，放在这里是它 inverse 的意思吧？啊，不是一个 phi 的。对，这样写才对。
对，
我这个比较喜欢找错啊。
对。因为会有 ambiguity， 你在指那个 B 的本身的那个 MAT 的 inverse。
你来给我出难题啊！我这个周六本来把契约了去芙蓉，然后我现在在想去芙蓉还是来跟你们去？
先看他们的车辆，然后开。
去芙蓉参加 Jason 的毕业典礼是？
哦，是啊，
是，所以
我没有听说哎。
我现在在纠结，那是你的问题。
哎，他们没有叫我，所以。
你跟 Jason 不是一样是人爱小组吗？
对啊，没有人在里面讲。
你被复利了，那就是。为什么你会不知道？你被
因为他每次送你们的
啊，
福音车每次送你们。
但是你们不是都是人爱小组？
对啊，但是我们比较少 meet 啊，就
那是你们的问题。
对呀、可能有趣吧，
但是你被孤立。
因为我上个礼拜也没有录这样。啊，没事，我要看。OK。
对啊，
什么？
这是一个 n cycle 啦。
嗯，
你是一个 n cycle 的话，你能拆成 n 个 cycle。一 n 减。
哎，
那如果我拿这个 inverse 它的整个是你自己在这个，
嗯，
代表说你拿它带它拆出来那边加 inverse 就减减加加就
没有你不管两边放什么嘛，它的数量一定是一样的。所以你2倍的 odd number 或者2倍的 even，它这就是2倍。
拿 sin
大家看，
sin 这种模型上来，
可以吗？
那我可能团队点还是那个它的 inverse 它拿不好inverse 它也不是
哦
省起来是1嘛，
，OK
它本来是减一个加，
OK，对
对呢，
对啊对啊，你这个看法就是我讲的，你是用科的，然后我们对 every 科呢都是 normal subgroup，因为你 apply sin 嘛，sin 是个 homomorphism 嘛，然后他们 evaluate 去 e 嘛，所以它是活在科呢里面。然后我们直接 prove 所有的科呢都是 normal sum。我讲的看就是普通的 definition 罢了。我乘一下，他们是 even combination，肯定吗？我两边都是，我两边不管我是加或加 even 啊，我一定是加2倍的嘛，所以就 even。
可能哦。
我是从 definition。因为我讲放到几点啊？忘记了。16分。那时可以讲一页的东西耶。哎，哦，要问东西。
证明这个东西是在看懂啊，拿过来。
Right. I mean, wait. Oh, wait. 我想想，是讲有这样的 case 吗？真的是一个 subgroup 吧？哎，喂，就但是这个 case 会 compare 这个 case 吧？因为你的拿掉的地方是 empty 哦，但是你还是可以选出这边有这边没有的。这个应该 cover 这个 case，但是这个 case 是就是就这个 case 哦，这个 case 会包含第一个 case， 2会包含，然后这个3应该是 negation。
就分开接
啊，分开写？
我觉得这样
没有，你就可以可以，你知道可以包含在那里。我们刚才用的 argument， 对，因为我从 H1 里面拿不是黑色的东西，那你这边更简单了，你里面都没有黑色的东西啊，我随便拿，所以就是它更简单。它这个是 MD 的这个 然后这个不一样，这个 case 是这是在 proof 另外一个 statement。我们要的是这个 statement，这个 case。Not P implies Q。你的是 P 来的 ，S3 是 P，它 contain equation one旁边。Hello。这句话要怎么？这句话应该是读得出来，直接读出来。这个 remark 是那一个 definition 会直接给你，但是这一个 equivalent definition 需要一点 proof。需要。
名校跟上面是同一个。
等一下 ，Hello。Okay, so let's take attendance. 小杨 ，Okay. 洪杰 ，Where's 洪杰啊？洪杰 missing in action. Is anyone 洪杰 friends or not? No 啊 ，missing in action. 康平啊，康平 no 洪杰啊。Can you track him down? It's not submitting assignment 哎。子明 ，Okay, I think I saw 子明。子航 ，Adrian 個嘉玲個子轩個 Lydia 個嘉玲邵琪Eugene Jasmine here or not? Jasmine yes. Albert 陳 B OK. 金魚浩瑞好。Hey 子豪 you say you want to find me? Have you solved yourself? 我们在哪里啊？下午113是那个 meeting room 中间那里，所以你还要找我吗？上课过后 ，OK， 在那个中间，那中间是113 ，OK， 那一层 ，OK， 那一层啊，last morning Tuesday morning you are not here, right? Can you usually attend the morning one or not? Do you have any other classes? No, OK。何心怡，心怡，not here。厕所 ，OK。修童 ，OK。冰夏，李冰夏，not here。冰夏，小月 ，OK。刘子涵 ，OK。洪瑞，一样。宇轩，OK。嘉怡 ，All right。方瑜 ，OK。嘉怡 ，right。姚林夕 ，I think I saw 林夕 ，OK。孙嘉怡 ，where's 孙嘉怡 again? Typically your Tuesday morning got class or not? Tuesday morning. You were not here last Tuesday morning. You 在咩 ？We have a replacement last Tuesday morning. 一起的没有点到孙嘉怡对不对 ？OK 好，孙嘉怡。谢长云 ，OK。严胜，Yeah。It's Eric。一凡呢 ？OK， 钟一凡。后面钟一凡在啊 ？OK 好。康平个 Rosie， 对，忘记去 ，sorry。赵胜的，这个是钟一凡，钟一凡是 you，OK。昊天 not here 昊天。丁信 ，alright。一行林一行 ，alright sorry 换位啊。修泽個修澤 Rachel 個唐鑫個林安個Ian 個鄭月個趙瑞個can you follow or not? Can you follow? Because you missed 2 lecture. I think it's a bit hard to catch up. Maybe you need to put some effort, or you come to a office hour. Okay. 金盆 right. 规则 yeah. 临近 not here 临近 oh 临近 okay. 临近 Tuesday morning do you have usual Tuesday morning because you were not here last Tuesday. 什么？早上有来吗？有吗？没有点到你名哎。哦，你有来啊 Tuesday morning 啊。Because I think Peter is trying to ask about this change of time again. So hopefully can change it before the concert. Yeah. Hopefully, yeah. And tonight no need to come anymore. Okay. Yeah, but without announcement, we still keep this evening time, okay? No need to ask me. I will announce if we change it. All right, so let's continue. All right, so if you notice that our speed will go faster a little bit because we will try to catch up syllabus. Not that I want to catch up syllabus, but our speed need to go back to normal. Because why I start slow at first, because I want to get everyone on the same page. I want you to understand what kind of rigorosity I want to get to, what things I am thinking about, okay, when I saw this statement. So you should apply the same thinking every time now, okay, now. But maybe I don't give you much time to digest or what, but you are actually better than the first batch of students that take AA1 already. Why? Because you already have previous year lecture notes. If you like, you should read it first. Okay, read it first. No need to understand everything, but at least has an idea what I'm going to say next. Okay, and then in the middle, when I'm explaining, right, then you think that, hey, this is the part that when I read, I confuse. Then you should give question already on the spot. Okay, then I can answer if I didn't explain in the class. If it turns out that, oh, after I explain, the lecturer explain, oh, I understand, then okay, it's good. If I still don't address your doubt, then you can point out during the lecture. Does it make sense? Understand what I say or not? I know it's hard to do, but do you understand what you need to do? You need to try and practice, okay? Otherwise, you need to train on spot. Okay, you need to train the skill on spot. Similar to if any one of you play music or not? Any one of you play music or not? How many of you play music? Instrument? 1, 2, 2 only. 3. 3 only. Do you read score when you play or you just play yourself? Do you read score or not? You can't pull. There's one thing called sight reading. Okay, sight reading means what? I give you a score that you never read before. You play on the spot. Sight reading. 直接读,直接玩的. Okay, so if you have this ability, 可以直接听,直接懂的, it's okay. If you don't have, then you need to do some pre-read first. Okay, do some revision first. Then slowly you will train your sight listening, not sight listening, but listen on the spot. Okay. This is a very important skill you need to learn as a mathematics students. Okay, because when you go to a math seminar, right, almost 100% you don't know prior, okay? Don't know about the knowledge prior to what the speaker speak. Because different people will work in different area. So you need to be on the spot, catch. What's the logic behind? Okay, you need to on the spot catch. Something that say doesn't make sense. Even though you don't know what they do, you still can catch what they say wrong. You believe in me or not? Do you believe in me? Even you don't know what's the thing that speak behind, but you still can catch the logic, what he did wrong. Yeah. So this is the skill that this degree can give you one. So Let's continue. All right. So next proposition. So we're going to prove the kernel of a homomorphism is actually a normal subgroup. Okay, so this subgroup is normal. So recall what's the definition of a normal subgroup? Meaning what? If you take any element inside the normal subgroup, okay, in this case the kernel, then we want to show that every G in G, the conjugate of X live inside the kernel also. Can you quickly see why is it true? I give you 1 minute. Why this GXG inverse live inside the kernel? Only from these two lines you can compute already. Give you 1 minute. Think how to verify something. And maybe we ask Yuxian, why is GXG inverse live inside the kernel of phi? What can you do to this element here? What can you apply? What can you apply? If you want to verify something is in the kernel of what? Kernel, what do you need to do? Kernel means what? Element that gets sent to identity. Under what? Under P. So what should you do to this element here? Huh? P of what? P of G, A, G, G inverse. But how to compute this? Phi is a homomorphism. So you can split all the way. But what is each of these? What is phi x? Where x come from? In the kernel. So phi x is what? Identity. But what is phi g inverse? Inverse of phi g. So you cancel phi g with inverse of phi g. So you get identity. Okay, so you evaluate gxg inverse to identity. So it's in the kernel. Okay. So hence gx g inverse is in the kernel of phi. Okay, so this is done. Another thing. So another thing is prove that every subgroup of an abelian group is normal. Okay. So if you want to write this inside into this into what logical statement, how do you express it? Abelian. How do you express it? For every abelian G and for every subgroup of this abelian group G, H is normal. So you see, there are two universal quantifier here. So meaning how to prove this? You need to start with what? Take any abelian group G and then take again any subgroup of abelian group G. Prove that that subgroup is No. Okay, so there are two universal quantifier hidden inside here. So, let's take hey. 打了，地震了。Okay, so let K be a subgroup of an abelian group G. Okay, we want to show that it is normal. Meaning what? So we want to show that what is this? K is normal. So how to show K is normal? We take any element inside this K and then show that if I conjugate with all the element in G, it still lives inside this K. Okay, so what? Let's take the element. So take a little k from K. Take any G, little g from G. Want to show what? Check that. G, K, G inverse is in K. Why? Why? Why is it in K? Okay, until this far, which condition we haven't used yet? Abelian. Okay, so this composition is abelian means what? I can commute. So GK G inverse is what? Good. So by assumption, GK G inverse is simply G inverse K, which is what? K. But you know K, where is K, right? K is in K. Okay, so we prove that GK G inverse is in. Okay, good. So done. Okay, so you see, one thing I want to emphasize for you is you can see that abelian group makes normal subgroup easy. What do I mean by that? You can see that this statement says that every subgroup of a abelian group is normal. Can you think of what's the difference between abelian group and normal group or not? So let's go back to this equivalent definition again. You see, this equivalent definition says what? Gn G inverse equals to n. But if like what what Zihan said just now, you can show that Gn equals to Ng. Hey, Gn equal to Ng says what? It's almost commutative. But be careful. This n is a big n. This is equal as set. So meaning what? It might permute. For example, what do I mean by permute? Gn1 could be N2G. Commute means what? Gn1 must be equal to N1G. So this normal subgroup are almost commutative already. Almost. So meaning what? If you are abelian what? If you are coming from an abelian group, obviously Gn equals to Ng. And then the equal, we will say on the north. 鼻子上面。什么叫鼻子上面呢？ If you plug in elements here, Gn1 must be equals to N1G. Must come from the same N1. But normal, we can permute. Okay, we can permute. Does it make sense? Okay, so you need to be careful. Equal as what? This is equal as set. So can permute one. As long as leaving inside in the other set, that's good already. Okay, does it make sense? Okay, this one is very, very super important. Okay, so if let's say we don't have abelian operation here, we will look for some abelian guy. So what's this abelian guy here? We will call the center of a group. So center is a noun, right? So you should expect some nouns here, some object here. So often we will denote by Z. Okay. So what's the center here? Of G, right? So meaning we must pick something from G here. So this is the set of elements that commute with every element in G. Okay, let's say we don't have commutativity on the whole group, but at least can we find someone that commute with others or not? Okay, so can we find someone commute than others or not? If you can, these guys are center, right? They are center because they commute with everyone else. Any center in your class or not? Any center in your class that can commute with everyone else? Pan Sing ah? Oh. So Pan Sing, not everyone's here. Okay, yeah. So this is an element that can commute with all the other elements. Okay, regardless what operation here. Okay, so we'll call this a center. So meaning what? In abelian group, who is the center? Everyone. Everyone. Everyone commute with everyone. Very happy in abelian group. Okay, if it's in the non-abelian group, typically you won't have this commutativity, but maybe some of them can commute with some elements. Yes, so identity is always a living inside the center. Okay, living inside the center. Correct or not? Identity always lives inside the center. Do you agree? EX equals to XE. Okay, identity always lives inside the center. Okay, good. So something you can prove here. So remark something for you for exercise. So one, the center is always a normal subgroup. Okay, it's always normal. Okay, go back and try this exercise. What we did just now. We show the group is normal. And then two is, yeah, almost the comment I gave just now. So a normal subgroup N of G is almost a center already. It's almost a center. Okay, it's almost a center. What do I mean by almost a center? So for example, if you compute things, if you take any element in N and any element in Z, what do you do? If you look at this guy, I forgot, let me write it down first. So if you conjugate your A with G, this is something else in N, right? Okay, but this says what? This says that GA equals to BG. But on the other hand, if you are in the center, what do you get? So on the other hand, what do you have? You have ZG equal to GZ. Okay, almost. Right, what I said just now, right? Almost. It doesn't commute. It commute up to something else. Actually, you see this kind of behavior before, right? 1, 2, 2, 3 equals to what? 1, 3, 1, 2. Something else. Not GA equals to PG. Yeah, but center must commute with everyone else. Okay, almost already. You see, almost. How do you see almost? The Z thing here. This Z here, but here AB is different, but here Z is different. Okay, almost. Right. Another thing you can prove is, I think we don't want to do it here now. So you can prove that every center Z of a group is an abelian subgroup. Okay, so it's abelian there. So meaning what? You take center composed with center. Center composed with center. Is it abelian? Center element composed with center. Because every center commute with all the group elements. Center is also inside the group. So meaning what? If you go to a non-abelian group, okay, you found center, and then within the center is again a abelian group. Last time I teach you a way to find abelian group, right? What's that way? Cyclic subgroup. Okay, so now you have two ways to find abelian group within a non-abelian. Abelian is nice, right? Do you agree that abelian is nice? Because you can freely swap their composition. Okay. Right. So let's see any example or not. So let's get some example here. So how about the center of XL2R? What's the center here? Who commute with everything else? Okay, so obviously identity have to be in there. And then the claim is the other center is minus identity. That's all. The claim is this. And maybe you can try and show it. I think there are exercises in the tutorial about the center here. How about center of Xn? Okay, we claim that there's only identity commutation can do it. Okay, for n greater or equal to. No other transposition cycle can commute. Or I mean, yeah, cannot commute with all group elements. Maybe you can commute with someone. For example, 1, 2, right? Can commute with 3, 4. But definitely you cannot commute with 2, 3. For gem. No. Center have to be true for all group elements. Does it make sense? Okay, it has to be true for all group elements. Okay, so here, this quantifier here, very important. Okay, not there exists, is for all. There exists story is different again. Okay, now it's for all. You are the center, ma. Okay, you cannot have anyone. Sorry. 没有想开车，但是不要讲。I mean, yeah. So you are the center, so you cannot. So you cannot not commute with someone else. You must commute with everyone else. Okay. Yeah. Okay. Good. All right. What time is it? 8:40. Okay, we can go on. Let's go on. I think we can safely go to isomorphism tonight. Okay. So next, there's very one interesting morphism I want to talk about inside your textbook. I mean the arting textbook. Okay, so this is a very interesting morphism I want you to look at. Maybe you go back and read it again. So this is a morphism from S4 to X3. Okay, so you need to try and imagine if I hand you a commutation of 4 indexes, how do you commute 3 things? How you commute 3 things? I tell you how to permute 4 things, but in the end you permute 3 things. Okay, how to do that? So a very interesting setting is like this. So first you have 4 things, right? Okay, so you have, for example, 1, 2, 3, 4, but you form 3 objects. Okay, 3 objects. How to form 3 objects? We form these 3 objects using these 4 indexes. So we set pi1, pi2, and pi3. Okay, set 3 objects from these 4 indexes. How to set? We actually partition these 4 elements in 3 ways. Can you think of how to partition these 3 elements in 3 ways? Okay, the way we're going to partition is a pair or subset of order 2. Okay, subset of order 2 means the cardinality is 2. Order of a set. Okay, I shouldn't use order, it's a cardinality. Okay, I will fix it. So each of these set, right, is a union of cardinality of 2 sets. Okay, so how to do this partition here? So for example, we can take 1, 2, union 3, 4. Okay, and then we can do what else? Let me give us more space here. What else we can do? We can do 1, 3, union 2, 4 here. Okay, the other one we will do 1, 4, union 2, 3. Okay, can you see that this is like all the possibility we can get? Okay, by partition 4 number into 2 set. So there are 3 ways here. So note that if you have a permutation in S4, what can you do? This sigma here for sure will permute the number inside pi 1. Okay, so give you an example. Give you an example. What example should I give you? Example. So let's say 1, 2, 3, 4. What does 1, 2, 3, 4 dig to pi 1? So what does 3, 4 does to pi 1? It permute the two number inside the same set. And then permute the two number inside the same set again, which is 1, 2 here. Okay, 1 to 2, 2 to 1. Okay, if you don't what believe, write down. So we get 2, 1 union 4, 3. But is this equals to pi 1 or not? Why? Because our set don't care about order. Right now we don't care about order. Okay, our set don't care about order. But imagine if you have another cycle, what happened? For example, 1, 2, 3, 4. A 4 cycle on pi 1. What happens? The 1 will go where? Go 2. 2 will go where? Go 3. 3 will go where? 4. 4 go where? 1. But is this pi 1 again? Nowhere. But is this something else? What is it? Pi 3. Wow. So what? What happens? You have a 4 cycle. S4 elements here. You permute among this 3 set here. Okay. So you produce a S3. If you don't believe, you can check, right? So how do we check we have a S3 element here? Obviously, you should check what happens if you do 1, 2, 3, 4 to pi 2 and 1, 2, 3, 4 to pi 3. Okay, so let's compute together and then see what we get. Okay, so what is pi 2? We move them down. Okay. Pi 2 is what? 1, 2, 3, 4. So 1 to 2, 3 to 4, and then 2 to 3, 4 to 1. So what's this set here? 1, 3, and 2, 4, which is pi. So let us bring pi 1 down also, which is what? Which is pi 2 again. Okay. How about pi 3? Pi 3, what happens to pi 3 if you do 1, 2, 3, 4? 1 to 2, 4 to 1, 3 to 2, 3 to 4, 4 to, sorry, what is this number? So 1 check already, 4 check already, and then 2 check already, 2 to 3, okay, 2 to 3, 3 to 4. But what set is this? This is pi 1. So meaning what? From 1, 2, 3, 4, what do you get? You are permuting what? Let's write these down. You send pi 1 to pi 3, pi 2 to pi 2, pi 3 to pi 1. So in the end, what do you get inside S3? You get the transposition 1, 1, 3. Okay, so you create, so we will write an arrow here. You have a 1, 3 inside S3. But this 1, 2, 3, 4 is in X. Does it make sense? So I give you a permutation in X4. You can create something in S3 by looking at how they set this 3 partition here. Obviously, you need to prove why it always works, but because of we include all the partition, the way of partition 4 indexes into 2 sets. 92. 写错什么? Sorry. Okay, thank you. Okay. Does it make sense? Okay or not? Another cool thing is who is the kernel? Who always fix these 3 elements here. 来，我让你们做一个练习，眼睛一直盯着这3个 set，盯住啊，不要停啊，盯住啊。OK， 盯住啊，不要停啊，听我讲话啊，你盯住啊。So imagine if you want to do the permutation just now 喂，不要打断我。Okay, look at this 3 set again Look at this 3 set here. Think, what is the permutation in S4 that will fix all these 3 sets? Meaning, if you do it on pi 1, you get 1 again. If you do it on pi 2, you get pi 2 again. If you're doing on pi 3, you get pi 3 again. Okay, so who is the kernel of this homomorphism here? What S4 elements will fix everyone here? Obviously, identity is in there, okay? There's more than identity. What do you think? Just look at these 3 things. Okay, who can fix all of them other than identity? It must be a permutation in S4. Right? Eric? I'll try. 哇，这么正式！不要站起来，站起来，站起来，站起来，站起来，给站起来。没事，没事，没事，没事。Okay, so what do you have? So 1, 3, 2, 4. So when he speak out these, try and apply this transposition to the whole 3 set. Does it fix all of them or not? And then why they fix? How they come up with this idea? And then? And then? 1, 3, 2, 4. Sorry. 1, 2, 3, 4. Okay. Does it fix all of them? Can you check? Okay. And then the claim is these are all the kernels. Yeah, thank you. Thank you, thank you. So you can prove that this is the kernel. This is the kernel, the only kernel of this. Okay. And later or tomorrow or future, we will see that this is actually isomorphic to the 4 order of 4 group that I gave you last time. Okay, in future, I will show, we can see this. I'm not sure we will do it together or not, but this one I put future again. Okay. Do you still remember this or not? Do you still remember this set here? When I draw the multiplicative table 0, 1, 1, 0, 0, 0, 1, 1. Okay. When I put here isomorphic, later soon I will tell you what is isomorphic here. But what I want to say here is they multiply the same way. There's a bijection between 2 of them. And then this is what we call the Klein 4 group. Okay, very famous group you have to know. Klein 4 group. Because there's really only 2 order 4 groups in this world. Okay, one is Z4, one is this Klein 4 group. Very, very important group in physics also. And this is what we call a Klein 4 group. Okay, so these are the only 2 order 4 groups. Yeah. Okay. Should we stop here? Stop here. Yeah. Okay, let's stop here. All right, so we'll see you on Thursday. And please hand in your assignment tomorrow midnight. Before midnight. Tomorrow?